Good afternoon, everybody. Today lecture, we're going to have two parts. The first part will be about the basic elementary signals, and the second part will be about the operations on signals, basic operations on signals. First, we're going to talk about basic elementary signals. What are the basic elementary signals? They are signals used to analyze systems. So if you have a system, it has input and has output. To test the system, you have to put input. So some certain signals are used to test the system. Example, the first signal, as you see, it's like unit step function, if I'm talking about continuous time signal. And you observe that it jumps from one level to another. For unit step, it's from 0 to 1. That's why I call it unity. But it can be from 3 to 4, 5 to 6. It jumps by 1 unit, whatever the unit voltage or amp. Is it important signal? Yes, it's important signal. Because sometimes we need to test signal systems, how they react for sudden change for the input. Like you have the switch for the light switch, then it's off on 0 volt up to 110 volt. How it reacts? Some system react in a way that's safe, it's fine, and doesn't overshoot. Some they overshoot. It depends on the components on the system. So signals shape is very important for testing system. As I said, the first one, unit step function, continuous time signal. See, it's 0. If the time below 0, negative, and start from 0, jump to unity, will be 1 all the time. If it's continuous, if it's discrete, you will have start from 0. When n equals 0, it's 1. N equal 1, it's 1. N equal 2 is 1. It's the same like continuous, but just take discrete time instant. That's also called unit step digital discrete time signal. And it's defined as you see here. For it's equal 1 when n greater than or equal 0. At 0 is equal 1 also. But n equal -1, signal is equal 0. So that's the unit step signal. The second basic signal, unit ramp. And unit ramp, the input is gradually increasing. When you say unit ramp, it means the slope is equal 1. It means every 1 second increasing by 1 unit. Can you have different ramp? Of course. I'm saying this is the basic signals. So basic signal means you can have ramp of slope 2. Every 1 second, jump 2 units, increasing rapidly. Possible, but we are talking about the basic, but you can modify according to the signals you want to test. What about the discrete time signal? Discrete time signal, you can have also unit ramp at 0 is equal 0, and then start to increase. When n is equal 1, what do you think the value is? When n equal 1? 1. Simply because you can, what's supposed to do, you replace, as we said last time, how you convert from continuous to discrete. You say T is equal NTS, as you did in the lab. So according to the time step, you can calculate the value here for the unit ramp. So it depends on the sampling time. So that's unit ramp, continuous and discrete. The third one, very important, used in the analysis a lot, unit impulse, and sometimes call it Dirac function. I think you have it in math. What is that? This is like suddenly change in no time, in very small time. Like if you get a hammer and then you hammer something like that, just in 1 instant, and that's it. There is no signal anymore. It's happened instantaneously, huge part. Ideally, you can say it's equal infinity in 0 time, but of course, practically you can have that. But this is the ideal impulse. How do you approximate it? You approximate like a rectangle, and this rectangle, the width and the height, in a way that the area is equal 1. That means the unit impulse. Let me show you what does it mean. So that's the ideal unit impulse. If this is the time 0, at t equals 0, we call it delta of t. How approximate this? We'll say for the practical one, at time 0, you can make like a rectangle. And this rectangle has width, let's say, tau, 0.1 second, 0.2 second, 0.01 second, very small, call it tau. So the amplitude A will be 1 over tau. Why? Because I want to find the area equal 1 to make unit impulse. So the definition of this one will be that like the integration of this function when tau getting closer to 0, was getting very small. So ideally, if tau is equal 0, the height is infinity. But I said this is practically never happen. But you can say t is equal 1 over 1,000 second. So this one will be 1,000 second. So the area is equal 1. So you can say that the area, that's the definition that we put in the last slide. We defined that the integration of delta t with respect to time from over tau, you can say, for example, that's if this is from negative epsilon and that's to positive epsilon, so what's the tau? 2 epsilon, right? So the tau in this case is equal to epsilon. So the amplitude will be equal 1 over tau, 1 over 2 epsilon. When you multiply, you get 1. The question is, you can have any shape of this pulse. You can have a small triangle or whatever the shape, but the area should equal 1. And the period or the interval of the signal should be really very, very small, infinitely small. So say if you integrate from negative infinity to positive infinity, the area should be equal to 1. And otherwise is equal to 0. So that will, it can say that and 0 otherwise. So this is only valid when during the period from negative epsilon to epsilon, whatever you can, from 0 to tau, whatever you can name it. So that's the definition of unit impulse, and it has special features and characteristics. Let me show you the first thing. But remember, the integration of the pulse from negative infinity to infinity. Strange, right? If you say the integration from negative infinity to infinity for delta t, it's equal to what? One, exactly. Because if you need the integration from negative infinity to infinity, from negative infinity up to negative epsilon, 0. And from positive epsilon to infinity, only the integration will be from negative epsilon to positive epsilon. So here is 0, here is 0. So the integration still, if you integrate it from negative infinity to infinity, still it's equal 1. It was only defined over this small interval. So that's first thing. The integration of it is equal 1. Well, what about if you multiply it by a constant a? So the value will be a. If you have 10 times delta, what's the integration of 10 delta? 10. Okay. Another thing, what about if I multiply, and that's very important characteristic for the impulse. If I multiply delta t by any function and you integrate it, what you're going to get? So if you multiply any function f of t times delta t dt and you integrate from negative infinity to positive infinity, what you are going to get? ft, exactly, ft. But there is something we have, f0. Why? Because delta t is defined at t equals 0. So if you have a function f of t and you have impulse at delta t, it's defined at 0. So when you multiply and make integration, so you will get this value at t equals 0. You get the function equals 0. Example. Let's say that you want to find the value of 2x cubed plus 5, that's a function, times delta t, and you want to find the integration from negative infinity to infinity. So what's the answer? Exactly 5, because you'll say it's equal to the function, which is equal to x cubed plus 5 at t equals 0. Because delta t only defined at 0. So that will be equal to 5. Okay. What about if this impulse is shifted right or left? What do I mean by that? Let's say we have delta t minus 3. How will we sketch that? Well, you will have a time axis, and that's 0, 1, 2, 3. So it will be defined here. That's delta t minus 3. Still, the integration of this impulse from negative infinity to infinity is still equal 1. But what about if you multiply it by a function f of t? If you have a function f of t, and you multiply this function by this impulse, what you'll get? You get the value of the function at this point, at t equal 3. That's right. So if I do the same example, I will have 2x cubed plus 5 times delta t minus 3. Delta t, the integration from negative infinity to infinity. That will give me 2x cubed plus 5. And evaluate this function. I'm sorry, I used x, I should use t. That's a mistake, should be t, the variable is t. 2t, 2t cubed, 2t cubed. So I substitute by t equal to 3. And I will get the value. It will have a numerical value. Just you get the value of the function, this one. Question, what about if I want to multiply the function by delta of t, but I don't want to integrate? What you'll get? Like, if you want to find f of t times delta t, let's say in general, minus t naught, not defined at t equals 0 at any time. You can have t naught equals 0, but in general, what you get? Do you have idea what you get? You will get defined at t naught, at this one, but multiplied by delta t minus t naught. So when you multiply only, you don't integrate. So you get the value of the function, you get pulse. This pulse, its height, the value of this function, because you're not integrating. So we'll not get the one. So example, if you want to have the same example, t2 u plus 5 times delta t minus 3, and you don't want to integrate. So we'll say it's equal to t cubed plus 5. Evaluate this value at t equal 3, and you put here delta t minus 3. So if you do what is the value of 3 times 3 times 3? Just 27 times 2. What you get? 54 plus 5, 59. So you got 59 delta t minus 3. It means you multiply only, you don't integrate. So you'll get the value of this pulse magnified, but the value of this function. It will look like that if you are multiplying here at 3, 2, 1, 0. So that's delta t minus 3. You multiply it by a function f of t. So the result will be this pulse, but equal to 59 delta t minus 3. If you integrate it, it should give you that only the value 59. Okay, so that's important to know about the pulse function. Okay. Another function or another signal, type of signal we are going to use a lot, rectangle. Rectangular pulse is defined, that's the ideal one. It's defined from negative to positive, and it's symmetric about the origin. And how you write the rectangular pulse, you say the period from negative tau over 2 to tau over 2, so the period for the whole pulse is equal tau. So this period is equal tau. And the height is 1. That's for the unit rectangular pulse. How you write, say, rectangle t over tau. It's function of time, t, and the width is tau. And since it's unity, you have 1 here. If you have 10, you say 10 rectangular t over tau. So that's how you represent the rectangular pulse. Do you have rectangular pulse in discrete time system? Yes, we do. It will be the same thing, but will be from negative n to n. So what is the width? We talked about that before. The width will be 2n plus 1. If you remember, because there is 1 at 0, we don't count. So say n minus n will be 2n, and then 1 in the middle at 0, 1. So that will be the width, 2n plus 1. And if you make the axis k, you will have k. Make it n, you'll be n, whatever the numbers that you are using, the integer number you're using here. So x of k will be equal rectangle, k over 2n plus 1, and it's unity, so you have 1 in front of the rectangle. Another one, that's the sine signal. And sine signal, as you see here for the continuous, when it's negative, we'll give you negative 1. The number is positive, give you positive 1. And we'll put it like that. X of t is equal sine. So changing the sign according to the sign of time. The time is positive, give you plus 1. Time is negative, give you negative 1. What about in the middle? In the middle, usually when you have piecewise continuous signal, what does it mean piecewise continuous signal? It means at specific time, it's changing its value. Like at t equal 3, let's say a signal equal negative 4 and positive 4, or negative 4 and positive 6, whatever. How you get the value of this one? The mathematician, the people working on math, somebody said, okay, we're going to take the average. So if you take the average in the signal, we'll say 1 plus negative 1 over 2, which will be equal 0, which is good for the sign. Okay. So it depends. I mean, it depends on the way that the mathematician will express it. Let's now look for the discrete. The discrete, you will have ones when k is positive and negative when k is negative, and 0 when k is equal to 0. So that's the sine signal. So that's all about the basic signal that you're going to use, and you will have exercises how to express. I will leave that to you to practice on this one. How you can express any signal using these basic or elementary signals. There are many ways. Like for example, we have here a question. I will leave you to think about it, Tom, and then I will wait for your comment or question. Like rectangle n over 10 plus 1. So that's a rectangle pulse, right? So can you express the rectangle pulse as a combination of unit step? Because maybe after I explain to you the operations and signal, it will help you. Do you have any question on the signals, basic signals? That way.